Good afternoon. My name is Dr. Claude Mallet from Waters Corporation, and today I will be talking about a topic that is, in my opinion, the novel aspect of chromatography, in this case, multidimension chromatography. It's perceived as a absolutely disruptive technology, kind of a Netflix effect, as I call it. Throughout this presentation, you will see that there will be a lot of statement that will cause a disruptive idea. What if? This case over here, you can see that Earth was perceived to be flat years ago, when in fact it's actually round. By disruptive ideas, you have one over here that I think is probably one of the best one I can actually found, is a scenario that we've changed drastically on how we entertain ourselves. Netflix basically came with some of the best technology, and without looking at disruptive technology, we have a scenario that one could remain complacent. Now, how does that relate to chromatography? Well, in this case over here, you'll see in the next few slides that a lot of users will see this type of issue happen. I need more sensitivity. Now, the problem with liquid chromatography is there's a scenario of mass overload and volume overload. So I have a very narrow window of opportunity to gain or actually produce a peak shape Gaussian distribution that I can actually utilize for both quantitative and qualitative analysis. If I inject more, I'll basically get peak distortions in the mass overload. When we try to mass inject a lot more volume or mass, we have what we call the shark fin profile or tailing profile for volume overload. So there's a limitation that we can do. The next aspect is I need more resolution. Unfortunately, chromatography is and will be needed to be connected to some sort of sample prep. A lot of sample prep will lead to very complex extracts. This leads to a scenario of how much entity do I have in a mixture and how much separation power do I get to separate. Now, depending on the type of application, a lot of time we have, as I explained, two concepts. I need more sensitivity and I need more resolution. So how do I do that? Next slide shows what chromatography is used for. So chromatography is a technique that we use to separate. It's actually sent to some sort of detection, could be optical or disruptive, but it requires to have some sort of workflow in front of it, sample prep. That's actually the dreadful scenario. I have to utilize techniques and protocols or methods to isolate the target analyte that we want to analyze out of a huge matrix complexity. Now, here I've actually separated the class in three classes, the type of sample matrix. Now, a class A would be considered a low matrix. Here we can see an example like drinking water. A class B would be a liquid solid type of mixture. It could be fruit juice, could be biological fluids. And the C class are basically solids. Could be tissue, could be a soil, could be food applications. But as the complexity of the sample increases, the task to extract said analyte, either for target application or screen, becomes really complex. And that's the 4-4-A method preparation. Now, the sample prep works something of this nature. There's actually at least 5 key steps that needs to be done. Before we start, obviously we have to collect the sample as we see in the upper left corner. Then we have measurement, we weigh, we transform a raw sample into an ideal format that either LC or GC can actually utilize. Now on the right-hand side corner, we have the extraction process, concentrate, we clean, we filter. And then we basically go through a solvent conversion that is compatible with a technique of liquid chromatography. In most cases, you'll see that most final extract will vary between 500 microliters to 1 mil, and the 2 mil vial or the 1 mil 96 well plate is basically the format that we need to put our raw sample into a ideal format that we can inject. That is basically a very lengthy extraction process. Now, when I started my career back in the early 80s, extraction was done in a very, very lengthy process. We can actually spend hours, sometimes days of extraction. This over here is an example of a setup that when solid state extraction came on the market back in the late 80s, early 90s, it changed radically how we do sample prep back then, but the concept remains the same. A lot of time we will need to do either an enrichment process, we'll need to do a lot of step to clean the sample and to have an extract that's actually of good quality that we can actually get decent results or satisfactory results. Now in this case over here, back in the early 90s, this is how I used to work with protocols back then. It was one, for example, for drinking water or water analysis, we would basically extract 1 liter, finish with 1 mil. Then this gives us the 1,000 to 1 enrichment process, of which we use 10 to 20 microliters for injections. In fact, we're using about 1% of our work for the final analysis. Funny, interesting is that 23 years later, as a savvy user in chemistry, I'm still using the same protocol. Technology has changed, mass spectrometry increased in sensitivity, chromatography increased in speed, but the sample prep remained the same. That's actually where you start realizing that when we look at instrumentation, for example, in the next slides, you'll see that traditional versus innovative. You will see that on the upper hand, that's how I was introduced back in 2000 when LCMS came to the market. A lot of folks will actually get best mass spec on the market, the best HPLC, and over the course of a decade, you have novelties in both mass spectrometry and chromatography, but interesting enough, in the sample prep area, we have exactly the same scenario. It hasn't changed. Now, where this will go, let's take a look at the next slides. Why is it that we can inject more? Well, it's obviously over here we can see that the 1D LC limitation, we have a serious injection volume issue. So now when we try to inject more, the system is actually choking up and we can't get decent peak shape, and it will become distorted, volume overload, and we also see a retention time shift, as we can see. Now, also, this is actually the standard aqueous extract or initial mobile phase. Most applications will require, or will use rather, a reverse phase type of chromatography, meaning that we'll start with a initial mobile phase in aqueous condition, most likely between 1 and 5%, and use the organic modifiers for a elution profile. Now, this is basically what happens to aqueous standard, but what happens if we try to inject a straight up 100% organic, as one would expect, we have total breakthrough. Why? There's actually no retention. Even if I inject large volume, it's not going to make any difference. I still and will always have a large volume injection, or this case, a breakthrough. So now we have here a scenario of what if those issues could be solved by a disruptive technology. And this is actually where, on these slides here, you're going to see that multidimensional chromatography, by adding extra fluidic circuitry and also adding extra component, will bring a novel aspect that a user can introduce or include in their workflow. However, multidimensional chromatography is not a new technique per se. It is a technique that's been around for decades, but it actually has a very bad reputation. The reputation at hand over here is when we go from a one-dimensional chromatography unit to a multi-D, there's two myths that I'll see, or one will see, coming up more often. One is it will be too difficult to understand, meaning that I cannot utilize this one. And the second myth is because of that difficult to understand, it will be very difficult to operate, install, troubleshoot, and produce decent results. Well, this is actually what this presentation is all about. So let's go into the heart of the topic. And this presentation is actually designed to give a heads up as to what is out there, what we would need to go, and some of the benefit of actually adding extra unit. In this case over here, entry-level multi-D would be as easy as adding one extra pump. If we want to go further, go ballistic, then yes, we can actually add more components. It becomes more complex, but with today's software, everything can be controlled. Now, the multi-dimension liquid chromatography option number one. So how do I increase resolution? Now, resolution is increased by simply connecting two columns together. Now, we're trying to avoid what we call these serial connectors. Now, in this diagram over here, in the middle, in the green box, I've actually put a standard connector. Now, what we want to do over here is utilize or introduce the concept of a separative dimension. What would actually avoid or actually give a resolution gain and avoid a coelution aspect? Now, there's several definitions, but there's actually two definitions of multidimension that basically opens up or actually comes more often. Definition number one, a resolving or separative dimension is any column chemistries with particle size less than 5 microns. So basically, we're looking at a high resolution separation. Also, there's actually a more relaxed definition, meaning that any dimension capable of a separation, either coarse or high, can be perceived as a bona fide dimension. So now we're looking also at a concept called trap columns. Now, in this case over here, we're trying to avoid any type of cell connection, because in this case over here, it will be the same thing as adding extra length. Adding length does not necessarily mean I'll have more resolution. Now, the predominant technique in multidimensional chromatography is what we call the dual loop injection, also known as comprehensive chromatography. Now, this concept here is interesting to utilize, but it's actually very fairly simple to operate and to understand. Now, the concept over here is that on the left-hand side of the screen, you're going to have your standard injection. One pump goes into a resolving dimension. Now, that dimension flow rate is purposely slowed down and will be diverted to an injection port on the middle of the screen that goes to 2 loops. Now, those loops will oscillate between loop number 1, the bottom, and the top one, number 2. So there's actually a fill rate of dimension 1 onto loop 1 has to be equal to the elution rate of loop 2 onto dimension 2. So now, basically what we're looking for is a multiple heart cut. So we're going to take a chromatogram and we're going to slice those chromatogram in distinct packet. It's called a duty cycle. So now the fill rate has to be equal to the elution rate. So now the second dimension will always be of larger ID with larger flow rate that will incorporate a dilution factor. Usually we'll have between 1 and 2 minute duty cycle. So what will happen is something of this nature. In these slides, you can see that we have here a very complex resolution on dimension 1, and we're losing, in this case, a very, very shallow gradient that could last 1 to 2 hours, depending on the type of resolution we're looking for. Then what we're going to do here, by setting up the second valve between loop 1 and loop 2, then we're going to oscillate between a flow injection rate and elution rate between the two dimensions. So now, by using a 100 microliter loop, in this case over here, we will have a 1 minute duty cycle. So we're doing a 1 minute cut at constant interval. What happens is something of this nature. We have here a typical contour plot utilized with UV detectors. So now we have the resolving dimension 1 and 2, and we have a top view of where your component of interest would be resolved. So now the contour plot over here, you can see that everything that has a high red value would be a separation, and all these blue region would actually means there's nothing there. Now, one aspect of comprehensive chromatography, in this case over here, it's a one of the first iteration of this technique, and we can see that it does increase the peak capacity or resolution capacity. Most time what happens is that you're still going to have a lot of tailing. You can see that in the bottom hand corner, peaks basically looks pretty wide. Now, this is actually nothing more than adding a resolution factor. It's pretty significant, but more can be done. In multi-D chromatography, there is a major impact that we can now start looking into really closely. So when UPLC, or ultra high performance chromatography, came in the mid 2000, it basically changed how one would do HPLC. Now, hour-long method were replaced by 5 to 10 minute applications. Multidimension will have the same type of impact that UPLC had versus HPLC, but it will happen at the sample prep area. So now, instead of actually spending hours and sometimes days of extraction, we can anticipate and look at applications as we go along in this presentation that will showcase interesting aspect and also disruptive aspect on how to operate and how to use these technology better. Now, the second option with multi-D is to increase the separation performance and the workflow. So in this case over here, we will add the concept of what we call a trap column. Now, a trap column is different from a anechoic column in a sense that we can see first, hardware is exactly the same. The only difference over here, we have what we call a direct connect, that we can basically reduce some of that volume, but the predominant aspect is the particle and the sorbent that these trap columns are packed with. Now, if one remembers your Van Diemt curve, or your the particle size will have a impact on your separation. So now, the lower the particle, the higher your separation power. Now, in this case over here, these trap columns will be used to refocus a part cut from a dimension, any type of dimension, and to allow a reinjection onto another type of dimension. Now, in this case over here, those trap column will allow to operate two resolving dimension in a static approach, as opposed to a dynamic that we see with the two loops configuration. Now, with a trap column, as opposed to a loop injection, we can spend a lot more time ensuring that a target analyte can be refocused properly with the proper condition before it reaches your second dimension. Now, in this case over here, we will see a couple of scenarios of how these trap columns are used and how effective those can be utilized in various different configurations. Now, the concept with a trap column, as the name said, it's not utilized for resolution. It's actually there for a certain purpose. Now, the first aspect of a trap column is that we can utilize this one in several ways. I'll explain as we go along. Now, on this slide over here, we can see that we have two chromatograms. The left one is a 100% aqueous standard that was injected into a single stream aqueous loading. Now, when we look at the chromatogram on the right, we have here a 100% ACN standard or extract. As to be expected, we see peak distortion. Now, what's the purpose of actually using trap column versus annual column if the problem remains the same? The aspect behind it is actually what's going to happen on the next slides. Now here, instead of using what we call a single stream loading, we're going to use what we call a dual stream. We will add a dilution factor into it, meaning that on the left side, you're going to see your injection loop. That's actually where you would put your extract. But before the extract reaches the column, it will be diluted to a ratio of about 20:1. That means that by manipulating, as it's seen in this slide, I have now a second pump. Now that's actually where the complexity perception resides. Where do I put those pumps and how many pumps can I actually control? This actually depends on software. But the concept over here is that we have a loading that will push the entire extract out of the sample loop and reconnect with a diluting versus via, I would say, a mixer. And by playing with the flow rate of loader diluter, I can now dial in a proper dilution ratio. At 5%, it means that anything that would be at 100% organic, it could be an IPA, could be an ACN, a methanol, an acetone, anything that's actually water soluble solvent would be dropped at 5% before it reached the trap. That means that we're in effect creating a isocratic condition. Now, the interesting aspect is that now that I have a dual stream loading with what we call it at column dilution, it doesn't matter if I have an aqueous or organic or any percentage of organic and aqueous. It could be 50-50, 25-75, doesn't matter, 100%. The compound of interest will be refocused in the proper condition on a sorbent that's compatible for the separation that comes further. So now, with this aspect, if we capture the chromatogram here, now we have a scenario that, in this instance, I have 4 chromatograms. The bottom 2 are single dimension. The standard 20 microliters, and I have a 250. Sometime by increasing the column's ID, I can have a efficient retention. That's not always the case. Now, when we look at a 2D system, basically is a trap and elute type of configuration with 2 columns. Now, if I use a single stream loading with 100% water, then I can see that the retention time will be a bit more longer. That's because of the dilution factor or the loading factor from the trap that has to be counted in. Now, by using an at-column dilution concept, we can see that we have a much higher loading rate, but it actually avoids any evaporation of dryness, as we're going to see in the next few slides. So now, this is actually water extract. We can see that every technique will give absolutely good results. Now, this one here is interesting because by adding 100% ACN extract, we can see that on the 1D, 20 microliters, on the 2D, 25 microliters, we basically have breakthrough, as to be expected. Now, with large volume injection on the single stream, we see we have a split peak on the third chromatogram from the bottom. Now we can see that that's basically means because the compound of interest is still surrounded with a lot of organic molecule. Now with the dilution factor of about 20 to 1, also we can see that in this case we can have a absolutely fantastic Gaussian peak shape, but we actually found a way to have a signal increase. So now when we look at sample prep, this becomes absolutely fantastic. So let's basically look at the next slides, and you'll see that with a multidimensional chromatography workflow, we can go into a sample prep and find ways on how to use this simple configuration for optimizing a novel workflow. For example, when we use a sample prep for the extraction of, let's say, a pharmaceutical or pesticide in drinking water or surface or water application, we would have in the blue box basically a scenario that we have to condition the sorbent before we can load the compounds. Because in this case over here, the conditioning and wetting step would remove any prospect extractable or leachable from the sorbent. Now, we have to remember this, not all SB sorbents actually created equal. There's actually a lot of manufacturers that will not take care on their not sample prep, but their manufacturing processes. That's the reason why we wash the sorbents first with very hard and a large cocktail of solvent to clean out everything. The ACN dichloromethane is just one of several. Move towards a solvent that's more soluble in water, and then finish with water that would be compatible with my sample of interest. Now we have a loading aspect. So now we're going to load our sample onto our sorbent, and also have here an enrichment process. So depending on the injection volume or the loading volume, we're going to look at this one versus what's going to be at the end. Now the wash step over here is done with various percentage of water organic. The wash step is there to remove impurities, interferences, but to keep the sample of interest locked on the sorbent. There's actually several techniques to do that. We can use a standard reverse phase step mechanism. There's also ion exchange or even mixed modes. With a polymer-based SPE, we can actually utilize what we call an air drying step to remove all water molecule out of the final extract, that we can do a much better and efficient elution. But the same process, it would reduce the amount of time to evaporate the organic layer and reconstitute an initial mobile phase. Now, this is actually where a lot of extraction will finish. It's actually a common point for reverse phase chromatography. Because we start with a rough or raw sample, it goes into an organic layer. That organic layer has to be brought back down to dryness and reconstitute an initial mobile phase. Now, usually the evaporative dryness and reconstitute can actually cough up about 40% of any extraction method. Sometimes evaporative dryness could take several hours. I've seen over the years application that will go up to about an overnight drying step, which is actually very lengthy. Now, with the fact that I can inject with a dual stream trap column combination with an alkyl column, now this large volume injection of aqueous and organic basically disappear. That's a disruptive aspect. So how can I use this? Now in this case over here, if I take my same method without changing anything, it means that I can take any aliquot of any step and look at real time what is exactly is happening. I can utilize either a target application. I can basically look at a target molecule, but I can also look at what else is involved with my compound of interest when I interacted with an SV sorbent. For example, on the condition, I can take the acetone, the methanol, and the water wash and analyze all those to see if there's any type of leachables that would be present in that particular sorbent. Then at all the wash step, regardless if they're water base or organic base, doesn't matter. Those can be injected directly without the need to evaporative dryness at all. Then I can take, in this case, two streams. I can take directly the finite elution and see if my compound of interest is in there, and also look at the final aqueous and look at the difference between an aqueous injection versus an organic extract. And a lot of time, this is actually where you're going to see issues with evaporative dryness, what we call evaporative loss, and redissolution problem. Especially for trace level analysis, usually an organic layer would actually and will give much better result. Now, based on that aspect, we can go in and optimize our extraction procedure. We'll actually see exactly what needs to be seen. Now, after all is done, we can also utilize Multi-D for extreme cost saving in terms of resource, time, and consumable. For example, the protocol on the left is the standard protocol that one would need to use with a 1D method. Now, on a two-column chemistry, or 2D as I call it, one could utilize a drastic aspect for multiple things. Now, because we can inject larger volume and organic and also aqueous, it gives options to keep the same enrichment process or actually increase the enrichment process while saving time. Because I don't have to evaporate dryness, I can actually take the final element and inject as much as I need to reach my injection level. So I can inject between up to 500 microliters, up to 1 mil if I want. In this case, if we elute with this application, we can anticipate that by eluting with 1 mil ACN from a 20 mil loading, we have in this case a 20-to-1 enrichment process. Now, injecting 100 microliters or even up to 250, it'll give a user multiple chance to do replicate injection from the same vial. In this case over here, we're using a lot more of our work. So the overall performance is that we can now eliminate the dry time, the evaporation step, reconstitution, and it also reduce the amount of elution solvent per extraction. Instead of using a 5 mil, we can use a 1 mil in this case. The enrichment process here is actually quite interesting to look at. In this case over here, we've injected, I set up a system that has both a UV detector for vitamin B12, and then I actually put the mass spec in series under scan mode. Now, usually PDAs will have detection limit at around 1 ppm. This over here is a 1 mil injection of a 1 ppb. Now we can see that PDA can see a very defined peak shape and confirm by the scan mode from the 1,000-to-1 enrichment. Now this here was an aqueous extract, and we have the exact same thing with an organic extract. So now we have choices, and there's actually choices allows to utilize several conditions for method development and actually create a methodology for applications. So that's actually where we're going to spend a bit more time on how to optimize retention. Now, In this slide over here, we have a two-column chemistry, dimension 1, dimension 2. Dimension 1 is our trap. Dimension 2 is our separation. Now we have here a concept of a loader-diluter pump. That's actually our first circuit for the trap. Now on the right-hand side, we have our injector loop that would come from the auto sampler. And then we add an extra switch valve that actually will create a connector between the loading circuit and the elution circuit. Now, each circuitry here will have conditions that needs to be addressed. Now, we need to understand how to load and how to elute, and we need to understand which trapping chemistries and which separation chemistries. Now, it could be a daunting task. If we look at the next slides over here, and then we look at these 4 parameters, we've looked here at a scenario that we have well over permutations that would be nearly impossible to analyze all of them, 400 plus. But what if we could start with the top 36? That gives here a starting point. These are the ones that I usually use for most of the application that I work with. And I start with what we call the 36 top methods that I will basically create into a grid called the 6x6 grid. This allows to understand and to go through the process of looking at how to optimize methods. Now, in the world of multidimensional chromatography, one will be confronted with the concept of what we call multi-residue application versus the concept of multi-method application. Now, multi-residue is kind of a situation that was a necessary evil because of lengthy extraction process. And it becomes very difficult to find several target analytes that behave exactly the same. Now, that's actually where multi-residue comes in. Because of sample prep being very complex and very lengthy, it becomes impossible to extract for every single compound in a single dimension. Now, with multi-D, since the sample prep protocol can be downsized by a factor at least of 10, perhaps even more, we can spend a lot more time or focus on novel sample prep and optimize sample prep according to a target analyte's condition. Now, let me explain. In this case over here, I've actually created what I call a method development. So it's actually a scenario that the system, any system that we have, can be automated to look at multiple target parameters. Now, depending on how much time we can use. Now, for example, in the blue box, we have here a scenario that we use 3 retention strength on the trap on dimension 1. So we use a low retention material, in this case, a simple silica C18. We use also in the middle C8 versus a C18 in the middle, and we use a polymer on the back end that has a lot more retention strength. Also, we're going to vary the pH, pH 3, 7, and 10. Now, that particular square will be eluted off the traps, or these traps, with a standard ACN mobile phase at low pH onto a C18 column. So now here we have 9 methods that looks at retention strength and loading pH on the first dimension. Now, when we would add a 3x6, we can add an elution from a low pH to a high pH elution, depending on the compound's structure, chemical and physical property. Now, when we add an elution polarity, we can switch from a ACN elution to a methanol elution. Now, depending on how much time we have, usually a 6x6 grid will take about 24 hours to complete, meaning that you have system with today's automation can run 24/7 without stop. So what do we get out of this one is something of this nature. Now, for example, In this particular scenario, I have a target analyte, which is basically a THC metabolite, in this case, AB Pinaca. And the aspect over here is that we have our first grid. So in this case over here, we have the 6x3. So from method 10 to method 18. So I have on the left-hand side my pH3, 7, 10, and I have my C8, C18, and polymer. So now I can see how this compound of interest will fare at any given time. So now I have, in this case, good resolution and good separation, or in this case, just a compound of interest, and I have good peak shape, but I can actually choose which method will give the highest intensity. So now in this case, I would actually chosen method 11. There's also method 17 or method 12, but anything that gives a high 90% can be chosen. Now, the extraction that was actually telling about between a aqueous and organic, injecting organic extract will have another level of sensitivity increase. For example, if I look at, in this case, a cocaine extraction from a urine or amphetamine, if I go from a water extraction final dilution versus a methanol and ACN, I can see that I have here a huge increase by going to methanol versus water. Now here, the aspect of how can we explain that one? This one is explained by the fact that at trace level, anything below ppb range, you start to have absorption issues on any type of active surface, especially glass vial. Once we basically have all these chromatograms, these results, we can create a method identification portfolio, understanding where the compound of interest resides. So by looking at a screenshot, in this case over here, we're looking at a microsystem application that we did a few years ago. This case over here, you're going to see that we have a water methanol and an ACN elution, final elution in this case. Now we noticed that on average between the aqueous extract versus a methanol ACN across the board, we're seeing about a 10x increase in sensitivity. Also, we're going in through the process of looking at every chromatogram and actually assigning a profile. So now, if we have a Gaussian peak shape, we can actually put in that method a green box. Anything that gives a signal, but would basically give either tail, lead, split, broad, would actually be yellow, meaning that I can see a peak, but it's not of good nature. I could probably use a method like that for identification, but most likely for quantitation. Now, a red would be a scenario that I see absolutely nothing. The challenge becomes at some point is to take all this data and put it into a scenario of which method do I use. Now, on average, by going with a 36 methods, you gain something around 85 to 90% success rate that you'll find a method that will work for any given compounds. Now, there's also a scenario that you'll have certain methods, certain compounds will not work. It just means that you have to go through another iteration of different sorbent, different chemistries, different loading conditions. But this particular scenario in a 6x6 grid gives you a good reference. In this case over here, when we look at the microsystem R, LR, YR, and the internal standard, we can see that we've taken out all these boxes that actually are yellow or red and concentrate on the one that gives the best methods or the best score. So in this case over here, we've chosen method 14. Because it gives the highest score. And we can see here on the right-hand side, a representative of chromatogram of separation for all three compounds. Now, the interesting aspect with this particular scenario of our injecting high-level sample and both aqueous and organic, it actually changes how we can do our sample prep. Now, in this case over here, the aspect of extraction development for maximum recovery, since I do not need to evaporate the dryness ever again, I can basically now spend some time on the optimization and look at polarity of my solvent, but also looking at my pH, and basically find on a quick experiment which method, which condition will give the best recovery. Now, in this case over here, we went through a process of actually evaluating at least 9 different solvents. More can be utilized. We simply do an elution and a loading, and we elute, and we inject up to, in this case, 200 microliters. Now, in this case over here, we can see that we can get a quick aspect, and basically we have a clean picture of how this compound of interest, a compound of interest, will react at any given time. So now in this case over here with amphetamines, we know that with a methanol elution works better than at neutral pH with no additive, either pH 3 or pH 10, better than ACN and better than acetone. So now this one basically behave as a polar compound. Once we have that, it's actually one way of actually looking at how multidimensional chromatography can have an impact on your workflow. Another aspect over here is that we can create what we call a sequential illusion. Now, this one is actually a very interesting application because in this case, we can have a clear picture of how a compound of interest is eluting off a cartridge. So it's not a matter of actually guessing, it's a matter of basically utilizing the same concept as a comprehensive chromatography idea, is to slice your sample into discrete packet and understanding where your compound of interest is eluting. So now, once we actually put all these results, in this case over here, you can see that you have multiple extract, but in the course of several hours or an evening run or an overnight run, all those results will be delivered the next morning. Now, by tabulating these results into a graph, we can see exactly how a compounds behave. Now, for example, RR starts eluting at 20% ACN on the low pH, but basically spread between 20 up to 40%. Now, at high pH, we can see that it actually has a tighter band between 20 and 30. So RR behave as a basic entity compared to a methanol at low or high pH. So this actually gives an opportunity, if compounds of interest behave the same, to find section between this graph as to what could be used for effective washes, but also effective elutions. One would not need to go up to 100% of elution, but basically go through a scenario that we can go at a lower percentage. That means that we can leave a lot more interferences behind and still lock onto the sorbent and basically just do a very narrow cut on sample prep for these scenarios. And in fact, we are doing here what we call hard cutting. The next stage over here, this one is interesting because we can go a bit more bold on our sample prep by using what I call a dual stage elution. So now in this case, suppose that we have very little information as to the type of behavior a target analyte could be. So are we looking at a compound that's an acid, a base, a neutral? Are these compounds behaving as acidics or basic? One would not know. So this one here could be utilized as a screening aspect. So now here we would end up with 4 final extracts. Now, depending on where the compounds are, we can actually see which one works best and which one resemble one another. For example, in this case over here, we have a anion exchanger on top, and then we have a cation exchange on the bottom. So now I have here 2 type of compounds. Obviously, they are pesticides from the organophosphate family and from the carbamate family. So they actually have an amine structure and a phosphate structure. So now on the MAX elution 1, we're talking about the 100% organic with no additive. Now the MAX2 would be the low pH elution to get everything off the anion exchanger. Now, MCX1 and MCX2 would be the reverse phase of the second dimension to see if there's actually any breakthrough. So now we have here a kind of an assurance that if it's not retained by the first stage, it would be retained by the second one. So now, if these compounds behave as basics, they should be retained on the reverse phase portion of the sorbent. So we can see that we have 3 compounds, on the other hand, that have a Zwitter type of behavior. Now the rest actually utilizes neutral. We have here a variable resolution rate between 75 up to 94, which is actually typical of what we could see for these type of compounds. But interesting enough, for a carbamate, even though they have an amine structure, some will behave as strictly as acidic. They're not retained at all in the reverse phase. Some will remain as neutral, as is both. Some will actually showcase Zwitter behavior, but one in particular out of the whole scenario has a basic functionality. It means it's not retained by reverse phase, and it's not retained by ion exchanger, but it's actually retained by the a portion actually breaks through in this case. So it gives kind of a really good idea of what multi-D can actually do. It actually gives us a lot more information about the behavior and the property, physical and chemistry of our TAG analyte. Now, those were actually aspect of how we can use a simple trap and elute type of configuration. There's actually multiple that we can do. Now, if resolution is actually the scenario to go, in this case over here, we have what we call a loop trap configuration. So we take a hard cut from my first dimension, and we can park it into a, in this case, a loop, and push everything of that loop onto a trap for peak refocusing. So now that means the dimension 1 and dimension 3, which are the high resolving dimension, can be operated independently from one another and is a bit different from the dual loop combination. Now this one here, the loop between dimension 1 and dimension 3 can be optimized for different applications. We can have a scenario that we're looking at, let's say, an HPLC high flow rate UV, and we can go towards a UPLC MS, for example. So that means that we can get a validated method in HPLC and get MS data without having to change the method. Now, for example, here we have on the left-hand side, on the red chromatogram, we have an application that was done on a standard C18 column under UV condition. This actually is a standard 4.6, 2.1 by 100 rather. And we see that peak H and K are basically eluting, are co-eluting together. So now on our second injection, you notice that we have the hard cut, and we can actually send that pair to a different column chemistry. In this case over here, we're using an HSST3 on one side, and we're using a phenyl on the other side to separate. Now, phenyl makes a lot of sense because in this case, these two target analytes are phenolic in nature. They have a very similar backbone with the difference between an iodide and a sulfur group, and we can actually separate those two better on a phenyl than on a standard C18. Another aspect over here that we can use is the same scenario. We have another coelution that happens in this instance, and by going from a C8 to a phenyl, we see that we have now structural isomers that basically can be resolved very well for this scenario. So now in this case over here, depending on how many hard cuts do I want, then I will have to add as much as loop injection. As a last one here, we can see that we have a synthetic cannabinoid. So now we're going from a standard C8 to a perfluoro application. So the concept here is the scenario that we can harness or hard cut, either a single hard cut or multiple hard cut for resolution purpose. So now this brings to the last slide, and I think it's actually a conclusion over here that I'd like to leave all of you with. The main issue that I've seen over the years when we talk about, well, right, actually, when I talk about the concept, it's this deep perception of difficult to understand or operate. And that's actually a scenario that it's not that case. Typical workflow today will have a very complex sample prep and usually will lead to poor performance. And that's actually where the scenario is right now. Single dimension chromatography has reached a limitation. So that's actually where the new analytical platform with a multi-component, multi-chemistry application or workflow will give you, in the end, a novel workflow. It means that you can anticipate looking at a technology of that nature that has a lot of benefit in cost reduction, time, resource, and consumable. It will optimize your sample prep protocol. Usually that will go from days down to hours, sometimes minutes. And it will also increase resolution performance. It's actually a very addictive technology. Once you taste this, you never go back. So this is actually, in fact, the presentation at work. Hope you enjoyed it. Thank you for your time.